Thank you, Adam, for the kind introduction. Good afternoon, everyone. Like I've been introduced, I'm from UCL Chemical Engineering. And I'm going to present our work on an EPSRC funded research project on digital manufacturing. This particular one will be on application of artificial neural network classifier for rapid identification of chemical reactor models. This presentation is going to follow this outline. I'm going to talk about the motivation and the objectives of this research. And it's going to be within an hybrid modeling framework. So I'm going to talk about the components, which are physics-based models, artificial neural networks, and we have used this in an optimal experimental design framework. And then I'm going to also tell you about the application that we have used this framework for and some of the results we have obtained before I conclude. Our goal is sustainable chemical engineering, and we want to use the available technologies, Industry 4.0 technologies that we have, including artificial intelligence, robotics, cloud-based technologies, as well as real-time optimization. Particularly, we are interested in digital twin technology, which is a replica of a physical system. And for this technology to work, it relies fundamentally on mathematical modeling. Just like most other Industry 4.0 technologies rely on mathematical modeling. And the framework we have adopted is hybrid modeling approach. We've heard in many talks the limits of machine learning models, and we are aware of the fact that these machine learning models, they are black box approximation, and we want to combine these two approaches and to leverage on their advantages. So the advantages including, the ability to advance process understanding, giving insight, as well as being able to extrapolate well. We are going to be using small calibration sets because we have our physics-based model already, which is able to supply large data set. And there is also room for fast development because of the machine learning models, as well as cheap computational resources. And then we'll be able to achieve our goal of sustainable chemical engineering. So just to talk about the machine learning models that we have used, there are a couple of them we've seen in this conference. Our focus is on artificial neural networks. We are interested in artificial neural networks because it can be used as a universal approximator for any function. And over the years, its application in chemical engineering has been increasing. And the focus has been on key chemical engineering processes to forecast, to design, and to detect faults, as well as for control purposes. In our group, we've also been using ANN applications. We have used ANN for classification studies, for reaction kinetics, and we have coupled these within an optimal design framework using a differential evolution algorithm to study theoretical experiments in a batch reactor. So the aim of this particular work was then to extend this developed framework of ANN DAA platform to flow reactors, to real reactions. So the objectives are to extend ANDAE to classify various reactor types. We talk of continuously stirred tank reactors, plug flow reactors, and anything in between. And by being able to represent these reactor types, we are equally able to account for the hydrodynamics corresponding to them. So we would also use this within an optimal experimental design to be able to recognize experimental condition where there will be least confusion about which hydrodynamic behavior is prevalent or which reactor is applied within that region. So I'm illustrating the framework of this methodology using this figure here. We have 4 modules making up the framework. The first is the physics-based model. So the first is the physics-based model. And then this physics-based model is able to generate as much data set as we want, which will now be used for the training of the artificial neural networks. And then after training, we would be able to check for further experimental conditions that would make the ANN performance to even be better. And that is where the differential evolution algorithm comes in to optimize the experimental design. And we can also use further design space exploration. And these will feed back into the physics-based model for further model recalibration and further model extension. So for us to have an idea of what a physics-based model looks like, there are 2 components. We have the reactor model and we have the kinetics model. In the reactor model, we are concerned about the reactor configuration. And in this case, we are inspired by a type of reactor which can vary from CSTR to PFR. So we could have different hydrodynamic behavior depending on the experimental condition. And then the kinetic model could also assume different pathways. In this case, it's been indicated using 3 different paths. And we represent each path using the Arrhenius equation. And by the time we combine both the reactor model and the kinetics model, we come up with the physics-based model that is generally formulated using differential and algebraic equation as shown in equation 1. So once we have different reactor configurations combined with different kinetic models, we will be able to come up with a model matrix. And we would then supply the design space indicated by this, and then the parameter space. So for each model, we would be able to generate results, simulated results. And so if we have this parameter space, we could generate different parameter sets from the parameter space to simulate the model for any reaction condition. And so that the simulation would be similar to what we obtained experimentally. We had measurement error model to it, and this measurement error is assumed to be to follow constant relative variance, and then it is assumed to be normally distributed following the Gaussian distribution. So this shows the table where what a typical data set looks like, in which case for each parameter set, we simulate all the models, all the combination of models, and then we generate data, responses from them, and then we would do the same thing for every parameter set. So in the ANN layout, we supply the input data, which comprises the concentrations. So we specify the network settings, the number of hidden layers, the number of nodes per layer, and then the output layer. And then we label each data depending on the model combination that has produced that has produced it. So this is a classification task. So the ANN is now able to connect the various inputs going through the output and then match it with the label that we have indicated. So the operations taking place for running ANN model is shown using these 4 steps, in which we have the input data, we have the data processing to encode different variables and to normalize and ensure that we have data for training and validation. And then we have in the network architecture the number of layers, number of nodes. We specify the activation function as well as the output function before we go ahead and start optimizing the network using the loss function, the optimizer, as well as trying to monitor the progress of these network training. The basic unit of ANN is a node. And this is just to illustrate how the transformation occurs within the network, and specifically the node, in which case the concentrations or the input going in are weighted and then biased before you use an activation function to convert it and transfer it into another form. And in the hidden layers, we have used the rectilinear unit activation function, which is able to make sure that our numbers within the layers are non-negative. And also the output layer, we have used the sigmoid activation function for binary classification, but for multiple class, it's softmax, which is a variant of the sigmoid. And in the optimization, we have used the Bernoulli probability function, combining different cases and how they are split between the correct data and the not correct data. So, but what we need to focus on is the ANN performance metric we have used, which is accuracy. This is what we monitor to see whether the network is performing optimally or not. And it is on the test set, making sure that we are not using the same data that we use to train the network for the performance evaluation. So, and this accuracy is illustrated using the confusion matrix. So basically, the numbers found on the diagonals over all the numbers found in the matrix will give us the accuracy of the network. And after training the ANN for a fixed experimental condition, we have also used this in optimal experimental design using the differential evolution algorithm, which employs the natural evolution for the sampling of the design space, experimental design space, and then it's able to generate the best species by selection, crossover, and mutation of the different combinations of designs, the different possible designs within the experimental design space to eventually come up with the best design at the end of the day. So we have applied this framework, the ANN DAU framework, for a quinary classification using the nucleophilic aromatic substitution. So in this reaction, it's pharmaceutically relevant, and we have multiple reaction steps taking place. So we have mono substitution and then di substitution. This mechanism that is illustrated is valid within the experimental design space that is shown using the lower and the upper limits of numbers for the different manipulated variables, the concentration of the first component and the equivalent concentration of the second component, and the residence time as well as the temperature. So we used kinetic model for this singular mechanism, because this is the only mechanism that is applicable within this experimental design space. And in the literature, we've already published some parameter values about these case studies. So we have like the parameter space also for this system, and we were able to use this for the generation of the model matrix. In this case, we have only one kinetic model, but we tested for different reactor classes considering their hydrodynamics. One is, when we have only one CSTL, we have two CSTL, we have 5 CSTLs in series, 10 CSTLs in series, and then finally we have the plug flow reactor. We have models describing all these reactors listed as shown in the table. So without adding any noise to the system, like I said, that the ANN is a universal approximator. So we were able to get perfect classification among the 10 classes. We have shown here that this required only 10 epochs, 10 iterations. And for this particular case study, we used 1,000 parameter sets in the parameter space. And so that means that in total, we had 5,000 data sets. For each data set, we had the concentrations of the component, which are 5. So, and then the other settings of the ANN are equally reported. But when we added noise, 1% noise particularly, we found that for the experimental condition that is shown here, the first experiment in particular, we started having confusion among the reactors as shown by the confusion matrix. We can see that the 1% noise is making the responses, the measurements, to begin to overlap among one another, particularly when we consider PFR and 10-CSTL. The gap, the difference between them are quite close, such that when we look at the confusion matrix for the actual, for 10-CSTL, you know, the prediction of our model was even the amount of prediction we got for 10-CSTL is less than that of PFR. So in this case, we have 101, which is more than, so the ANN classification model was not able to recognize the data set for 10-CSTL in this case. But because we have an optimal experimental design framework, we then searched within the design space to see if the performance of ANN could improve. And we did that. We were able to move from 30% accuracy for that first experiment to 84.1% accuracy. And we can see the corresponding confusion matrix indicated. And then we can also see what the space distribution of accuracy is for the space distribution accuracy is for in the design space. I would like to point out that for this particular case, you can see that the maximum accuracy that we got using the Latina hypercube sampling was around 73%, but within the optimal design space, we were able to get something even higher, that's 84.1%. So, in conclusion, we have developed in our group, we've developed a model, a hybrid modeling framework, and we have investigated it, and we have applied these to a reactor model types with the hydrodynamics, as well as employing this within a design of an optimal design of experiments using the differential evolution algorithm. We will further do some sensitivity analysis of this framework, as well as go ahead and apply this for digital twin implementation, also for real-time optimization of experimentation. And we are also currently looking at physics-informed neural networks for the specifically identified model for this, for any case study that we have of interest, that is of interest to us. I would like to acknowledge the funders as well as my colleagues from the Galvanic System Identification Group, and I want to thank you for your attention, and I would like to get some questions and feedback from you. Thank you very much.